All right, welcome back. I want to show you a neat little visualization tool that's available on the web here to kind of help us understand what the central limit theorem is saying. So let's just real quickly reread the central limit theorem. If x bar is the sample mean, it's the mean of a random sample, size n taken from a population, the limiting form of the distribution of x bar, that should say of x bar, the limiting form of the sample mean x bar is standard normal. The limiting form of the distribution x bar minus mu over sigma over root n is the standard normal distribution, okay? The important thing is that x bar follows a normal distribution, which once we subtract the mean and divide by its standard deviation becomes standard normal. And this is true for populations that are not necessarily normal. So let me go ahead and tab over here. This is from the Seeing Theory website from Brown. If you just Google Seeing Theory and Brown, you should get a website here. It includes a lot of neat visualizations for common probability and statistical topics. One of them, of course, is the central limit theorem. So what I'm going to do is I've got a nice looking normal distribution here. Okay, so pretend that this is my population distribution, and we're just going to go ahead and say that it's normal. I'm going to draw samples from this distribution. Let's say samples of size 10. All right, I'm going to do one draw at a time here. And I'm going to take a sample of size 10, and then it's going to plot its mean on the line below. Boom. Okay, so took a sample of size 10, 10 random points from this distribution, and it plots the mean. All right, let's go ahead and do it again. Notice that this sample mean right here, it looks pretty close to the mean of the actual distribution, but it's maybe a little bit south. That's a little left of it. Let's do another one. There's another. Okay, here's another mean. All right, there's a different sample of size 10. We have a different mean. This is what we're talking about when we say the sampling distribution is we plot where all of these means, these sample means go. So let's go ahead and just up this to 50 draws and have it do it a bunch really quick. And it'll plot all of those. All right, so 32% of the time, we got a sample mean that was in this area, and 28% of the time, we got a sample mean that was in this area. We can see that this sort of starts to look like a normal curve itself. That's a normal curve, looking curve itself there, right? In that the distribution of the sample means is normal itself, and the average of that is the true population mean, okay? That is the true population mean, all right? Now, if we want to get an even better sample, we should infer, for example, from the central limit theorem, we can reduce our standard deviation down here, right? If n becomes larger, right? This is as n goes to infinity. We take a larger sample of size n, the smaller the sampling variance, or the smaller standard deviation should be. So let's go ahead and up our sample size to 15, which is not very large, but still, you know, more than 10. And look at how much more narrow this becomes. Look at how much more narrow this becomes, right? An increase in sample size, we reduce our sampling variance. If we go ahead and just take samples of size 5 or 4, for example, we're going to get a lot wider of a distribution, but still something that looks normal nonetheless, okay? Now, the cool part about the central limit theorem is that we don't have to be drawing these estimates from a normal population. So let me go ahead and change the skew or the distribution here of our population. So that's still, let me make this look quite a bit different. There we go. That is certainly a curve that would not be, we wouldn't say that's a pretty standard normal looking distribution curve, right? But let's go ahead and take samples of size 15. If we had to estimate where the mean of this should be, I would probably say just visually it should be somewhere around this neck of the woods. And let's draw 50 samples, and let's take a look at the distribution of our sample means here. There we go. There's our distribution of our sample means. Notice this distribution is still approximately normal. Notice how that distribution is still approximately normal, regardless of the original population curve that it came from, right? I can toy with this even more if I want to. Let's make this something completely different. Let's see, I would change my betas here. Something more like this. Again, very much not normal. there we go. How about that? Some sort of exponential looking distribution, okay? Definitely not normal, but we take samples of size 15, we'll draw 50 of them, plot where those land, all those sample means land. The distribution of the sample means is still approximately normal. Okay? That is the power of the central limit theorem. And hopefully this helps us visualize the difference between, or what we mean when we say sampling distribution, and how the sampling distribution is approximately normal, even though our original population distribution is not necessarily normal, okay? If you want to go ahead and play around with this on your own, again, like I said, you should be able to Google seeing-theory.brown, and you should be able to get there. It's a very cool website, and we might show it up in later videos too, as I see interactive demos that fit for our learning purposes here.